Okay, so maybe we get started for this lecture. So we are going to continue about the LLM. So now we are looking at the post-training instruction tuning. So if you recall last time, we talked about pre-train fine-tune framework, right? So and that is more general for encoder or encoder decoder or decoder only. And you the fine-tuning on specific tasks. Things evolve a bit, and eventually it becomes in the modern LLM becomes instruction tuning. So the purpose is to train a general purpose language model so that it can follow human instructions. So basically, this is essentially the goal. So yeah, so the outline, we will talk a little bit about the post-training pipeline, the general ones. And then we will specifically focus on the instruction tuning. In particular, we'll mostly talk about the data because the tuning itself is just fine-tuning, basically. Yeah, it's just supervised fine-tuning. So the main question is where the data come from. So this is something we will focus more on. So we will go through a few papers about this, which is representative. And then we will talk a little bit about the scaling in this post-training or instruction tuning, or also called SFT, supervised fine-tuning. Right? So basically this stage. And then that's about it. So so basically, it's a more general introduction. So you get an idea about what's going on, other than some detailed mathematics. So if we look at the pipeline, right? So we know there's a pre-training. Basically, you just train next token prediction on a vast internet text, and then what you do is after that you learn the basic structures. We mentioned about fine tuning last time, which is try to make the pre-trained knowledge into more specific knowledge to certain tasks. For the post-training, it's a slight generalization of that. It's kind of a fine-tuning, but you are looking at much more data, and you try to give additional capabilities of LLM through this pipeline. So so you have a pre-training or post-training. Post-training usually have two stages. One is instruction tuning, which essentially can do chat. So if you think about what the pre-trained LLMs can do, if you try to communicate with the LLMs, they will not be able to do chat very well. They do not know how to follow instruction. Basically, don't know what you want at that time. And then instruction tuning will allow you to tell them this is actually what you want, then that the LLM will be able to do chats. There is also RLHF, which we'll talk about later. It's a reinforced learning human feedback. So this is usually for the alignment of LLM and the interest you have. Basically, it try to do reinforced learning, make sure certain objectives are essentially met, like you want to be helpful, you don't want to be harmful, you don't want to be basically rude, and so on. So yeah, these kind of things, it's a little bit difficult to constrain that for the instruction tuning. therefore you still need the additional alignments. So that's typically after instruction tuning. And then you have this model deployment. This is simply pilot pipeline. Now there's more, so I will comment a bit. Also, the instruction tuning sometimes now the boundary may be a little bit blurred because instruction tuning, those kind of data, because those are just data, specialized data, it can go to the pre-training stage. So therefore, in the modern pipeline, there are variations about that. But just from conceptual wise, this is essentially what happens in the traditional setting. Pre-training is on a large text data set, right? Instruction fine-tune on human instructions. So this is more to do with what human wants. Basically, it's pairs. You have questions, you have answers, then they will learn what kind of answers you want from from whatever the chats. This one is again, it's more about refinement, and you want to encourage a certain behavior such that your response will be more aligned with humans' value or humans' expectation, and so on. So deployment, then you just deploy that, for example, ChatGPT and so on. So this is basically the pipeline people generally use. Certainly, there are more to that. Things evolve. For example, the reasoning models, right? They require RL training of reasoning abilities. This one again is started with OpenAI, the O series, and now it actually all the models support the reasoning, and they require more RLs. And even more further one now is agents and so on, right? So they also have a specialized models which needs to be for the coding agents, like they are tuned special. But those are so basically things are evolved. But even with the evolved thing, this general pipeline is a reasonable approximation. So for whatever the purpose about training LLM. So essentially what achieves, right? I think I mentioned this, but I just want to emphasize it here. It aligns pre-trained LLM, which usually if you start to do a conversation with a pre-trained LLM, it really doesn't do too well. They don't know how to respond to some desirable fashion. It just tell them to follow human instructions. Usually the data will be prompt response pair. So prompt is a user's question. User asks something, and the LLM will answer. So this pair of then they will tell you, what kind of response is expected for questions like this. So basically, this is a type of format. It will align behavior. Basically, they will try to learn what you want, the user intent, what you want to answer about. You can. The other thing about the current instruction tuning versus the traditional fine tuning, a little bit. This one can be regarded as fine tuning, but it uses a diverse set of tasks, which we'll comment on later on. And then once you go through a diverse pre-training, then plus a diverse set of instruction data, then you can actually transfer to new tasks. So this is something very interesting. Basically, they have a generalization ability once you do the task generalization. Right. So the key part about the instruction tuning, again, just once you have the instruction data, tuning data, you do a fine tuning on instruction data. So that's more or less it is. So the key part is pre-trained model to instruction tuned model is the data curation. So this is probably we will talk more about. for the class and just give you a flavor of how these data are created and what effects they have. Yeah, and what we need in terms of this kind of data. And then basically once you go through that, you go to RHF and so on. So let's talk a little bit about data formats. Basically data formats is like prompt response pairs, right? So this is what we mentioned. I mean, this example is like this. What is the capital of France? And then you say Paris, but you have other questions. So this is a flavor of data. It's really more like mostly one round. It's chat data, communication data, right? At least traditionally that's the case. I mean, you can talk about multi-turn or whatever. Those are more advanced, but generally this is what it is. Apply after that before the training. Learn instruction following the task adaptation. I mentioned the tasks, which we will say more later on, the tasks. Basically, it quickly adds a useful capability before the RL. So, and RL can do more things like usually it's alignment, which is RHF, or you can also do reasoning, right? Reasoning is something which people put a lot of attention. This give you more capability, and usually those are trained using RL techniques. Yeah, the key things which will come back again for this instruction tuning will be when you measure the data, right? First is of course the quality, right? You do not send in garbage, right? You're sending garbage, then that's basically instruction tuning data usually will be of higher quality than the pre-training data. Pre-training data sometimes data quality also matter, but sometimes you can get a little bit not necessarily always all quality. Also, you can get harmful things in the pre-training, right, and so on. But once you go through this stage, you want to make sure the quality matters. Quantity is always the more the better, always. But the more important than the quantity is diversity. Diversity is actually what we will see later. Some graphs and so on. We will but essentially there are three things: quality, right? Basically, this is easy to understand. It's needed, and then you have good number of such data quantities and diversity. So diversity much to do with tasks. So when you say I have a diverse, if I have more tasks, then usually it's more diverse and a different type of task. So this is actually how the data diversity is generally controlled by using different tasks. So I can give an example of that task. There are diverse set of tasks, right? Each task actually you can have its own prompt response pairs. It's just a certain kind of problems. Traditionally, when you do fine tuning, you do specific tasks. If you do BERT, you say pre-train fine tune specific tasks. But then for instruction tuning, you put a lot of different tasks together, and the more the better. And then you have to create those tasks. For each task, you create a different prompt response pairs so that you can prepare your instruction tuning data. Example task is summarization, right? So you have a document. You can have a classification, could be an example, but a summarization is another example. You have an article as your input prompt. You have human written summary. It's a shorter summary, right? As an output. And then you say, okay, train model to predict the summary from the article. Basically, you just continuous train from the prompt. You say, give a summary, right? If you say, oh, give a summary of this article in your prompt, that essentially to generate the summary. And if you are doing instruction tuning, you could do these pairs. Pair is article. You have to say what you want in the prompt, right? What task it is. Task you say summarization is a task. Then you just describe that. Then they will output your your human written summary. Basically, this is an example of task. Of course, you have different articles, different summaries, and therefore for this kind of each task of these, you can have a different prompt response pairs. So you train from many different models. Once you trained, right, it's a better instruction following. They know, oh, when you say summary, this is what you want, right, basically, and what kind of summary you'd like that to see. Also, because you're talking this summary and this was done, they know essentially specialize for this task. And once for specialize this task, it certainly has much cheaper than full pre-training. Right? Typically, full pre-training, it's terabytes of data, right? So it's a huge amount. Instruction tuning usually depends on the time. It can be like 10,000, 100,000 to million, or those levels. Those are the instruction prompt pairs. But those are generally much smaller than the full training. And at that level, you already learn things, basically. Yeah, even at the level of say 10,000, 20,000, and so on. Even at that level, you already learned a reasonable amount of instruction following. So you can learn that actually pretty quick, especially because they generally know once you pre-train the language model, for example, for summarization, they generally know. They just somehow, if you just tell them to give instruction without instruction tuning, usually not do that well. But once they see few examples, continuous train, they will fine tune their skills so that they actually know what is expected. Task diversity is pretty essential. This is actually where the diversity actually comes from, mostly from task. And also, of course, you can have within tasks, you can have prompt response diversity, but the task diversity is pretty much what we need to control. Once you have diverse tasks, this is where you can lead to task generalization. Some unseen tasks, you test that. You can argue that because you have similar tasks, you generate that. So it's like a coverage of all possible questions you expect to ask, they expect you to answer. So basically, yeah, this is something which diversity can bring you. Is this task generalization? How do you create that, right? So we basically talk a little bit about how these are created. Those are not very complicated. It's just it's experience which people have gathered, have tried on, and so on. So there are two primary sources. One is human curated data. We will give examples later on, and there are papers talking about how they are created. Then you are seeing that So essentially, task you first you say, okay, what task it is, right? And then given tasks, you create some instructions, create some responses, and so on. Another one is LLM generated. It's a self-instruction. Basically, you try to instruct using LLM created data. Turns out that also useful, even with that, especially when you filter out some undesirable response. So it can self-boost. So this one becomes much easier, of course, because you can generate a lot more. But it turns out that's also a useful approach. You have seed instructions, right? You generate more instructions, you filter out some responses, and you iterate and you put some things. So basically, this one gets you much more. When we say like million level instructions, usually those are not human created; those are automated created. Those kind of instructions, there are open source ones available. Okay. So this is about instruction tuning. So let's look at the human created. This is based on this paper. We'll talk about another paper, which is this one actually, yeah, is the supernatural. I think there's a natural instruction we'll also quickly talk about. This is after that. But essentially what it does is, right, you first you give that task instruction, task definition, right? You say, oh, given this, if you read this, given something output yes, whatever, if this one and no, and so on. So this one is a kind of tasks. And this task, then you have a positive example, you have explanation, you have a negative example, then you give an explanation why that's all. Of course, explanation can be regarded in the this one is if you see that is like 2022, so it's before the people join reasoning, right? Explanation essentially you can think as an internal reasoning of the model, which try to produce your output. It's like a chain of thoughts. So but basically, this kind of format, one type of format, then you will be using, and then you try to, based on these instructions, you create a lot of these pairs, and then you essentially try to leverage that. So prose is certainly high quality. When they say high quality, it's a human created, right? It's not it's at least there's some quality control. Domain specific. You can do different domains of this. And sometimes people train like for specific domain for legal or for finance, you can create you can boost more examples in those domains. And it's most reliable, right? So that's a cons. Of course, one thing clearly is it's pretty expensive to get this kind of data. This data not cheap. And it's basically human has such bandwidth, so you cannot create a lot of that. So the quantity is an issue. Basically, I think that this all to do with this scale. Because of that, people shift to this LLM generator. So LLM generator, how does that work? Basically, LLM generator gets following, right? So essentially, what you say is following. You have instruction, right? You come up with zip code, and basically this is kind of a you can call that a task instruction, right? And then your input is something, output is your zip code. So basically, and you have this, and then essentially you ask you give the instructions. You can ask LM to generate. We will talk more details. Generate the instructions, right? We can also talk about generate inputs. In fact, we'll go through this paper later on, and you can also have a code segments, right? Write whatever the code, and so on. So basically, yeah, all these instructions you use LLM to generate, and then you basically use that. So you can generate quite a bit with certain format. Prose, of course, is generating instruction data is it's scalable. Cost effect is comparable with a human, right? You can generate a lot of this kind of instructions easily. The cons, of course, quality may not necessarily always be there. I mean, they have always issues like hallucination or sometimes response not quite right and so on. Although human has these issues, but hopefully it's better in the simple tasks. But basically, therefore you need some more quality control, especially for these kind of simple problems, like which human as well. You need to require some filtering and post-processing. This is what talked about in the self-instruct paper. We'll go through a little bit more details, but basically, yeah, this is also there could be a little bit of bias because typically LLM has certain flavor. You probably know like when they write. Sometimes they partly because of RHF, they try to be specifically flavor, or partly because other reasons, and this could be further propagated. So that's another issue could happen. But generally, because it can generate a lot of more instructions, So this one is certainly used in addition to the human data. Basically, yeah, this is certainly what kind of a mixture you have generated human, maybe modified and so on. This is very easy to scale. This by the way, you can also is another way to do that is using the large model to distill smaller model. Basically, you can use a larger model to generate this kind of question answer pairs. This one used also quite a bit, and then you will train a smaller model which is more cost efficient. You can easier to deploy so that you deploy certain scenario. So basically, one way to do that is that. But even you just using your own model to generate evaluate your own model, this is still a doable approach. In addition to use a larger model to distill a smaller model. So let's look at the key factors in instruction tuning. I mentioned already quality is important, right? So this is at this stage, you do not want low quality data. It's not like pre-training. Pre-training, you can allow low quality data, but not at the instruction tuning. You need a lot of data. Turns out that it's much smaller than pre-training, right? When I say millions of pairs, it's really not that big. It's if you compare, I mean, millions of even you just say to the large example, let's say number of tokens is probably a few hundred million tokens, right? Then at the level. That level, or even you just say 1 billion token, right? It's a level because pre-training is trillions of tokens. It's tens of trillions of tokens, so it is a huge difference, maybe 10,000 magnitude difference. Diversity is important. This one we will talk more later on when we talk about scaling, when we talk about some of the work and their experiments, they all demonstrate this. The diversity, especially for the task diversity, right? You want to have task instructions. At that level, you want some diverse. You don't want to see all the problem look similar. In that case, you know, quantity doesn't matter. Okay, different tasks and different instruction types and so on. So basically, diversity matters. Okay, so this one is important. Natural instruction. So this one I will quickly one example of human curated instruction. Then we'll talk about the supernatural instruction, which was shown earlier. Essentially, you know, this cross-source human written instructions. You have 60 NLP tasks. It's reasonably large, right? It's have 200K instances. So and then you have basically, you know, title, definition, example, and constraints, and so on. Basically, I'll just quickly go through this data. Then we'll talk a little bit more about the supernatural. That is, it's a follow-up of this paper. The result you have basically at this level, you already can actually learn instruction. So, but here is a follow-up to that, right? Just supernatural instruction. You have more tasks. The claim task is 1,600, right? So if you look at what these tasks here are the examples, right? You have translations, you have question answering, you have question generation, you have name entity, you have all kinds of NLP tasks, and entailment. Those are the classical ones. They roll back from the birth arrow. But they put that. Therefore, you know, the LLM will be able to learn the grammar structures, or at least the meanings of something. So basically, you know, this kind of different tasks is what they are looking at. They just generate using a lot of linguistic background to generate all kinds of different tasks. It's a 1,600. Roughly, right? And there are task types, then that's a smaller language and so on. But they also have multi-language, another thing, right? Usually you want to have a different that. So basically, if you look at that, it's quite a bit of data, right? So yeah, essentially it's a larger data. It's definitely a larger data. than what is before. And this is more or less human created data. And this data actually can be used to train LLM to the instruction following data. So basically, if you compare with what happens with natural instructions, basically, you just have some comparisons. Essentially, it's become large. So main thing is it's a large compared with the earlier version, and then that's. So here is an example. So you can see what actually and there are of course many of for example there's a task type, right? Task ID and definition, task definition, right? Basically, it's a causal effect classification. In this task, you are given two statements. You must judge. Second is the cause of the first one. So it's like somewhat like reasoning. Label the instance as cause or effect based on your judgment. This requires like a really natural language inference or inference in the sense of the causal effect inference. Right? Really need a true understanding. Before the LLMs, this regard a pretty hard problem, even for the birds, for whatever the even earlier models, right? Early. But after LLMs, this one becomes much easier now. So it more or less can be considered more or less solved. Yeah. As long as you have knowledge. But basically, yeah, this flavor. Essentially, the LLM actually learns what you really want from this kind of questions. And also certainly the flavor of these kind of questions. That's essentially what you learn. Because a lot of knowledge probably comes from pre-training, not from this instruction tool. So first thing about the woman met for coffee. They wanted to catch up with each other. The question is cause or effect, right? So basically the second sentence is the cause. They want to catch up with each other, so they met for coffee. Basically, so yeah, it's a pretty subtle. You have to to really understand the language, and clearly the modern LLMs can. So the explanation is like this. Yeah, the other one is my body casts a shadow over the glass and the sun was rising. Effect out of this effect, and there isn't an effect of casting a shadow of the glass. So yeah, so basically, so essentially this is. But anyway, so yeah, this is kind of a flavor. This example that essentially the given these examples, right? You want to ask essentially this is kind of describe these definitions, and it's like in context learning that then you essentially you class valid output of a woman tolerated her friend's difficult. A woman knew her friend was going through a hard time, right? Because go through those hard time, therefore tolerate. So basically, so it's cause. So that so basically, these are type of questions. Certainly, there are many such questions. They need a lot of efforts to create, right? Basically. Yeah. Okay, so they are looking at one thing which I mentioned, because you can look at the scalability. We will come back to the scalability later on as well. But for this data, they want to justify why they want to create a larger data than before, right? So then they want to understand the scaling of this training data set and with also not model parameters and so on with their accuracy in the basically response. They use a certain short, essentially, measure the similarity. Right now, people use the LLM as judge. It's different, but at that time, 2022, they use traditional metric. ROG is for generation, traditional metric. We will not talk too much about that, but basically, it just measure how close your generation is to the human curated generation. And then they see some results when you have a training task goes up. It's good, right? Number of instance per task. Turns out if you look at that, number of instance per task is not nearly as effective as what task. Diversity. This is where this is quantity, right? So this is diversity. So this is why diversity matters more than quantity. Yeah, because they are too similar. This one, and then this is what you actually get. Yeah, and the model size clearly has a significant effect. So this we know. So larger model better. But anyway, so yeah, so this one demonstrated. We'll come back to this with other experiments, which is similar conclusion. This one is also part of this is Google's data, which is also pretty big and it's a popular data. FLAN collection. So it's a collection of public data designed to support generalization across many NLP tasks. Basically, it's released by Google. There's a FLAN T5 model, which is a T5 that using instruction tuning. Get it FLAN. FLAN is basically this instruction tuning data, and that teach T5 to T5 is encoder decoder mode. T5 to do the instruction tuning. Follows scaling tasks and the response enrichment techniques. So they do something, task scaling, mixture of zero shots and so on. Basically, they talk a little bit about this data mixing, so we can try to see what they try to say. And this one is good when you do, I mean, this kind of ideas actually relevant now. I mean, even relevant when you try to fine tune your LLM to other tasks. Because if you see how they do, how the experiment they do, like diversity, like what did they try to inject this, and the idea can be borrowed to other places. It actually is useful. So this this is their paper. They have another paper which is related, which we'll talk about more talking about scaling. But here is the paper. They have essentially they are looking at different. I said T5 and T5. Let me see. There's a FLAN collection training. But okay. I'm trying to basically this is basically what they say. All the data is available right here. There's a FLAN and there's more natural instruction and this one and so on, and the supernatural instruction and so on, right? Yes, self-instruction is later. This we'll talk about. This is LLM generated, a representative work of that, and they have these models and so on, and they have size of these data and so on. So okay, anyway, so although this is I think this is a model size. This is not size of data, data collection, all kind of. So basically, this is what they basically. One thing is question. They basically ask a few questions to their data, right? Few short prompts. This one we will say a little bit more, but probably at this time we all know, like we're just adding examples, just like the natural instruction, a supernatural instruction. They give some positive negative example. They can put it into the prompt as your few short examples. And essentially they try to understand whether you add these few short templates at training, how much it helps, right? And how much it's how much it is, right? So basically, I think the conclusion is the following. So few shots, essentially when you use few shots to evaluate in the held in data and held out data, just different tasks. Held out, they use MMLU, which is a very standard benchmark, which is essentially is kind of a high school, university type of all kinds of question answering for the different classes like algebra, like geometry, like chemistry, and so on. So it's a scientific discipline. It's like exam questions, those kind of questions. Those, of course, could be corrupted into the pre-training, but nevertheless, when you are not looking at too much, you are kind of this typically being evaluated. One of the evaluation metrics for the LLMs. Now maybe get a little bit obsolete because it's over tuned, but nevertheless still is useful. And when you look at this evaluation, right, basically tasks is not trained on this data. They trained on this data is kind of flat. So meaning if you have a few shots, does it improve? Basically, if you have a few shots improve, meaning they learn what a few shots means when you put additional few shots data into your training. Basically, that's the application. So all they are just the application studies. When you add few shots data into my training, instruction tuning, what will be my effect on my MMLU? This is so that's essentially the conclusion. Another thing is scaling with the task and the model size, number of tasks. Here, yeah, held in, they don't see too much different because held in is just training data with training data. When you have more training data, you evaluate training data, it doesn't matter as much. What they are interested in is out of task evaluation. So all the machine learning nowadays, if you think about the traditionally, they think a single task, you have a training head out. Actually, our homework was like that. You have training held out, and then you train. So essentially, they can be all considered as an in-training performance. You just head out the questions, but not the tasks. But here, in the real world, it matters you are shifting your tasks, right? Your tasks are slightly different. Like you're never trained on these university exam questions, but you give them, they could perform that, for example. So this is MMLU, and they see some improvement. So when you have different tasks, which then you see more probably related to this. You can think about this way, right? If you have more task, they cover a lot of different types, and then this one get cut. So task, when you have diversity, it matters for generalization. So these are not really take-home message from that. It is still true. Yeah, even for other tasks you want to create or benchmark, whatever. So if you want to create those things, try to do task diversity is important. It will generalize better. That's another thing, right? So this is consistent with the supernatural instruction. Yeah, single task fine tuning on held out. Basically, they try to understand whether you're fine tuned or not fine tuned, right? So will that matter? Right? This guy can be considered as a pre-trained. This flan is really instruction two, right? So basically, you can think about this. So this is solid instruction two. As you can see, instruction tuned. It's a better starting point. They better understand your instruction. Or even by the way, this for T5, this encoder decoder model. You should expect this kind of experiment would hold for LLM as well. Right? So LLM is decoder only. But still, if you look at that, so it's better. But once you have more and more data, they gradually converge. So essentially, you can think about instruction tuning, give you a diverse set of these kind of few shots, the kind of small data, such that they are boosted stage. But with more and more few shots data in your or fine tune, actually fine tune, single task fine tune, you can still use. So this one has a difference of generalized LLMs. When you say for certain problems, right, it may not necessarily be competitive on very specific narrow tasks to a specially tuned. So that's basically you can see, especially for certain tasks. Yeah, some other tasks is different, but here are the examples. So, but that instruction tuning you have better throughout. Right, so it dominates your pre-trained model, even for the fine-tuning task. Basically, it's always help. tuned model. This is a base model without instruction tuning. So that's another thing. Okay, so now let's look at these, right? So basically, they try to understand the input inversion. So basically, this is also created diversity in some sense, just ways of generating different type of tasks, right? You have inputs to target. Basically, this is a prompt. This is your response, right? And basically, they say, okay, I have a question. I have a chain of thoughts, which is thinking tokens, thinking, right? So and then you have reasonings. You have then you give an answer. I have a question and give you a reasoning thought, the trace, ask you for answer, right? I have a question answer. Then you infer what is the reason about that. What is the explanation about that? It's just like what in the supernatural instruction they have this question answer. Then they have explanation. So where you have to say, if given trace, can I revert this question? So essentially, they're just making a mixture of different things. Question, answer, chain of thoughts, right? So basically, they say, okay, what you can do with that, and then the question is, can you actually, can you actually learn something there? So basically, you essentially this one says that this one will improve basically, and then they're talking about different creations of data, right? Different creations of data and then how they can improve. This are another thing which use typically you want to have a weighted different data. And turns out weighting sometimes matters. Therefore, a lot of reasons why weighting matters. This is all data, and this is some other data, right? So and so on. This minus, right? Minus to see how the effect of the data, and then you weight that. So if all equal weighting, and these are other data, they try to do the instruction tuning or and then you have these guys, right? You have these guys, and then you say, okay, if I add a chain of thoughts, what do I do, right? And then essentially on the chain of thoughts data, what it performs, and also on the MMLU. MMLU probably is more of matters. Roughly speaking, weighted will be better. From weighting, you can see what is important, just minus, right? You have all the data minus this guy, drop is high, which means this data is important. This is Google's data, it's itself data, plan 2021, right? This is a huge job, probably more than that. So clearly, so what's interesting is here, it doesn't seem to help. I don't know, I mean, so maybe it's already covered by other data for some way. But nevertheless, so because this is more important data, so that you can weight this, and then you try to get this. And there are methods that you can create. How do you train this weighting scheme to have a better validation? So, but essentially, data weighting properly, putting more important weights to the more important data will be. Of course, how to create weighting is another thing. That's a more specialized topic. You can either by hand or you using algorithm to do that. Plan contains multiple data sources, right? So basically, yeah, and the proper mixing requires get a better result. So this and this very very typical when you do this kind of real world model building. Weighting controls quality, and basically the higher the better ones, like flan here, right? Clearly has more important, right? Mixing improves the quantity and the diversity. So you as long as you can do a better weighting, you can do better. Even everybody get the same data, basically, weighting would make a difference. Okay, so Now let's move on. This kind of is a human generated. So we will later come a little bit back to this the scaling, but there are some overlapping. But essentially scaling, we'll talk more. But here we will talk a little bit about the LLM data. So when you do LLM generate data, self-instruct is one approach which is pretty standard. They generate instruction following data without a human intervention or with a human filter data. Roughly, this is the process. And we'll see more examples later on, but roughly this is the process. Start with a small seed set of tasks as an initial task pool, right? These are task descriptions and so on. Random tasks are sampled from the task pool, and use that in-context examples to prompt Esme to generate additional tasks instance. And filter low quality or similar generations, and then you iterate. So this one may be either you need another LLM or you need the human to do that. So basically you have to say, oh, what is low quality? Then you maybe transfer your model to do that, or you have a human to do that. But or similar generations, right? So you need some model to do this. And then back to the task repository, and then you iterate. So basically this iterate process, you have usually this one you can have a human generated, right? Human generated. The more modern way, I mean, to do that, to be honest, would be reinforced learning, right? If this one actually, if we later look at reinforcement, it's a very like a reinforcement learning loop, in the sense you start with some data, right? You generate with this data. This one is a so-called reward model. You just filter automatically using a model, machine learning model, or using verifiable reward to filter out the low quality data, right? And once you do that, you add back iterate. So if you treat this as a model instead of human, this is a RL type of approach. Okay, so yeah, here is a there are about 175 C tasks, so one instruction, one instance per task. Okay, then you have a task pool. Step one, you instruction generation, you give a task, right? Instruction, give me a code from famous person on this topic, right? Then this one is they're specific. Nowadays, probably this can be managed basically because they differentiate tasks to be task types. One is classification. Classification, you ask for discrete labels, right? Whether it's positive or negative. One is not. This one clearly is not a classification task. So it's no. Then you give a code from famous person. Then topic. Then generate a topic unit, right? So topic is the importance of being honest. The output is whatever. Basically, this is something like something like this. Okay. Here is what are the classification? Classification is pro-abortion, right? And you have a general text. Text says, I believe that a woman should whatever, right? And then you can ask the classify is a pro-abortion or it's anti. Right? So basically, that's yeah. This one you can also generate. Basically, you ask, they are generated. Essentially, you can give the response to generate a question or give a question, generate whatever. Basically, you want ask ML to automatically do it. Filtering, this is where you go back, right? Filtering is if you consider this is as reinforced learning, then this one is a reward model trying to leave out the bad data, keep the good data, and so on. Then you iterate, basically. So this is the way it's done. Yeah, here is a prompt is what you do. Yeah, we might give a homework on this because this is pretty interesting homework. So we might. So one homework, then you just go through this data generation method. So yeah, come out with a series of tasks, instruction for existing task 1, instruction for existing task 2, instruction for each task 3, and so on, right? And then you have to say, basically, this one is given. This is a random sample. This one as in context examples. Then you ask to continue, ask LM to continue. So the model is allowed to generate instruction for new tasks, right? So in this new tasks, essentially this one try to bootstrap tasks, task descriptions, instruction for task. Instruction, for example, this one to give whatever for the famous code for whatever the topic, and until it stops, right? So reaches last limitation. This actually has a danger of generating tasks that are similar. So this that's why you want to filter out something. You could have this case, but you want to say, you want to generate new tasks, right? And not then you have to tune your prompt a bit. If we measure that from the self-instruction data, right, we have 3 dimensions. One is quantity, diversity, and quality, right? And basically, you start with C. There's a little bit more than 167, I believe, right? So that's the instructions. They start to generate 50,000 from that, and 80,000 instances. So they generate quite a bit. So from that, just bootstrap by a lot. And in the internet, a lot of data generated like this. Basically, they use a different task, different whatever, using GPT automatically generate. Usually, they because this research in the open source community is popular maybe 2 years ago, right? So most data were 2 years old in the sense of they were generated at that time. A lot of data was generated using this kind of approach, basically, similar approach. And they also aggregate together. They try to filter out some. They have some of the instruction data are pretty good, actually, pretty reasonable. If we redo them now, maybe we can generate better data, but probably not too much because if you think about the chat, right? So largely it's done at roughly that, and the more recent is moving to the reasoning and the agentic rather than the chat, right? So basically, therefore, people are not paying as much attention to that now. But still, this data has been around open source using this GPT to generate that, and they turns out to be reasonable. At least at the first approximation. If you want to fine tune that, then you have to do much more work. Probably beyond open source will do. It has to be closed source. So you have to really have the user dialogue to do more complicated things. But many new instructions were generated with a limit overhead with the seed. Filtering is needed. You need some, but definitely much faster than human generate all those, right? You just filtering, and so it's in fact, you can train a reward model to that in RL, so that would be even less so was a human generation. Yeah, so basically they try to do an evaluation, right? Quality review questions. Does the instruction describe valid tasks? 92%, because some may be not really valid. Is the input appropriate for instructions, right? 80%. Is the output correct, consumable, and so all field valid is 50%. In fact, you have to remove quite a bit of data, in order to make a high quality data set. But basically, this is where their statistics looks like. Okay, so that's that's about what this looks like. So, any questions so far? Okay, So yeah, self interaction compared with human curated data, right? This is they want to justify to say self-instructed data will be as good or at least comparable or at least it's a reasonable approach. So this yeah so if you look at this, right? So this is a vanilla GPT-3. GPT-3 at that time, now I think they already removed a long time ago, but at that time there were models, OpenAI release API after their GPT-3, right? They have the GPT 3.5 was ChatGPT, but they also have a vanilla GPT models which are not ChatGPT, not being instruction tuned, and they are trying to compare to those. Yeah, so this and they are actually for this doesn't have a lot because they are don't know who they are training, and this guy is this is one of instruction data, right? This is another instruction data, super instruction tuning. And then they say, okay, let's move my self instruction. This one, so you still have a human there. And it's definitely will improve. If you look at this, they claim is they are improved, right? So here is without even super instruction. So without any supernatural instruction, and then you get this. So this is something they show, and yeah, these are the yeah, these are the instruction GPT, but the instruction GPT is it's more or less ChatGPT. So it's or maybe it's earlier versions, but there's paper about that, and clearly they describe this pipeline. So mentioned and including RI chat. So they are certainly doing a better job, of course. I mean, this OpenAI have a closed source, right? This guy is just the open source reproduction about what they are doing. Yeah. So basically, yeah, basically, instruction GPT could do better, but the pipeline is similar. So essentially, their claims is the human generated versus self generated. Self could be even better. So, and I mean, this is one of supporting evidence, but people do try. I mean, therefore, there's a bunch of self-generated ones, instruction tuning data nowadays on the internet, much less human generated. Much more than basically more than human generated one, self-generated. So let's finally let's talk a little bit about scaling. We already talked about that, but we will say better. We will also talk about the scaling law following this. This is a more general, just scaling different size, but this is an example, right? So you're scaling what do you want to scale, and the different ways you want to scale, and their relationship, and so on. Better result by scaling up. SFT is just instruction tuning. So in here, it's the same thing. This one is the same as this FLAM. It's Google paper, similar to the FLAM, but it's just more focused on the scaling rather than focus on the instruction tuning. The FLAM paper is more focused on instruction tuning. Right? But again, they are very similar because this one also try to do the instruction tuning. But they are interested in the tasks, model size, and fine tuning of chain of thoughts. If you see that they are probably similar, that's why. But it's just a different emphasis. So here is what they are looking at the scaling model size. For scaling model size, and the task numbers, right? So do you increase? And these are held out tasks, right? Remember, in the earlier paper, they showed that they are similar in the held in, but they are more interested in the held out. And if you look at that, so when you model size goes up, right? So it certainly goes up. Model size actually matters more if you look at this, right? Basically, but yeah, even you say small model has but instruction also helps, right? So these different lines are just the different tasks. These are small number of tasks, no fine tuning. This is the base model. You have 9 tasks to add, right? You get. You have 89 tasks. You have more tasks, right, to get, and eventually the more tasks, the better. Although the difference will be smaller when you have a larger. So this is what they are saying, yeah, from this. And here, yeah, just different tasks. When you have task increase, what you get. Okay, but nevertheless, number of tasks matters, and the model size matters. So this is not surprising. Then also you have SFT with non-COT data plus COT data. The question is whether it improves the performance. Held out data, COT, right? So here is yeah, here is yeah. Turns out it has what is mixture. What is interesting is let's say I have a COT, right? COT, if you have held out its COT, right? It has improvement non-COT to COT, right? So and the best is non-COT plus COT, okay? Non-COT plus COT. But here is non-COT, right? And here is COT, right? Here is non-COT plus COT. So basically, the conclusion on non-COT plus COT better, at least for this experiment. Basically, they try to understand the reasoning. Of course, the reasoning now is treated a little bit differently now. But in the instruction tuning, you can put this reasoning chain of thoughts into that, right? And here is what it looks like for the COT for the COT. So if you have a COT for a non-COT head-out benchmark, it doesn't really improve. So it's worse than non-COT. So the best of both worlds will be you have non-COT and a COT mixture. So again, it's a mixture, data set mixture. Basically, once you have a mixture for the task of non-COT, they are similar. For the task of COT, they beat, right? This beats. Yeah. So basically, yeah, this is a story. Say you do a mixture of COT and non-COT. Data mixture also increase diversity. So that's where also one way to think about it from diversity perspective. Similar to the task definitions, number of tasks improve diversity. COT, non-COT also improve diversity. So you need more diversity. They have instruction tuning, and yeah, this is different test set, and this one, basically, yeah, and this is what they are doing, and task categories and the total tasks and so on. Yeah, I think one thing I want to say, basically, yeah, this is about what it says. So eventually, you know, I think for the plan papers, these two papers somewhat similar, but essentially, you know, they all try to answer the questions about when you create this kind of data set, what matters, right? The real conclusion from this, if I'll just say the simple conclusions, right? You want to increase data diversity more than quantity, and the diversity can be measured in the task. Is a very quick way to classify diversity. And within task, you also can have other dimensions like COT, non-COT, and so on, or different subject would be one, right? And so on. So I think I will just quickly mention this evolution about thinking from this task-specific fine-tuning to instruction tuning. If you look at that, the task specific, that is before the LLM, which was, for example, in the BERT or in the earlier days about natural language, or maybe 5 years ago, right? They will say pre-training. At that time, pre-training fine-tuning is established, but pre-training for task specified. Sec to sec, task specific models, encoder decoder trained for a specific task, right? This is one example. Each task typically requires a separate fine-tune. So then you need a lot of different models for different tasks. That's order thinking. If you really want to deal with a lot of models, that's a challenge, basically. Example is, this is a translation and so on, right? And then later on, the T5, it's already pushed similar, actually, because Flan T5 was working with the T5, right? Text-to-text framework. It's all task cast so that you do multitask learning, instruction tuning, right? Task identity encoded as a prefix. Basically, you are trying to say what is actually your task is doing and so on. Essentially, you just say basically this is like prompt, right? It's already a prompt. So what is your name? And then you give a prompt and then this one is encoded the task and so on. This one is already pretty similar to instruction tuning. It's already same. At that time, the starting point, if you look at the Google paper, the starting point, they want to do multitask learning. And later on, they gradually realize when you do the multitask learning, you can have out-of-task generalization ability. So then it becomes general purpose. And nowadays, it's a really kind of an evolution from here. It's just more focused on the general capability of LLMs when you really do this instruction tuning, right? So basically, you are training very diverse sets, and your model learns generalized to unseen tasks, basically. Example is basically whatever, right? So, but anyway, so I think at this point, from instruction tuning wise, this is become a standard pipeline. Essentially, it's a little bit more about data generation. Therefore, quite some bit of instruction tuning once you generate the data could fit to our part of the pre-training stage already. So it's a blurred a little bit of pre-training and fine-tuning. But it's a really, if you look at the thinking, it's really just from specialized tasks to more general. With that said, there are some advantages of training specialized models, right? Especially for the small models, they do not have such general capability. Therefore, you can train a small model to achieve on a special task to achieve performance better or equal to the larger model. That's possible, right? So essentially, people still doing that for certain models, right? For example, you want to do specialized domain, you have your special data which is not in the open source, meaning that maybe GPT doesn't have that data, right? So then you say, okay, what do we want to use that data? Maybe using that to fine tune my model, and so and this is generally what we can do. So so coming back to the current stage, right? We will still do the instruction tuning for a lot of the LLMs. Let's say you are domain-specific LLMs, but it will also train with domain-specific data as well. So let's say you want to consider a legal domain, finance domain, whatever domains LLMs. What you do is you do a pre-training. This one is already given, right? It's general data. Now, let's say you have special data, you believe they are probably not there, or you believe you want to emphasize those data, maybe they don't learn as well. You want them to be more focused on this data, then you train on this data, and then you do this instruction tuning could be related to this data. So you can do a mixture of that. right? Because start with this guy and the stuff that and this instruction tuning is more domain specific ones. It's not the general one. So then you can still do a specialized. So basically, but the framework changes slightly bit. There are general capability models, but if you want, you can still try to fine tune it. Also, you want a little bit more general. You do not want to be too special, because when you be too special, what happens is the following. A too special model is hard to generalize. If a user asks a question slightly different than too specialized model, then it actually will fail. So you want to be a balance of generality and the specialization. So basically, yeah. Yeah, so these are papers we talking about, and I think that's all for today. Okay, thank you. There's a question. I see. There's a data set between pre-training and instruction. Actually, instruction. There are not a lot of difference between that. Therefore, instruction data now are going to the pre-training. I mentioned that. So now the line is blurred. All right. Yeah. So you could merge the instruction tuning to the later stage of pre-training, not the beginning stage. So that's also very typically done. There are not too much difference. That's why we are talking about how you create this data. This one. So how do you create those data different? Now the pre-training, you just grab your data from the internet. And this one is specialized creating. Okay, I think that's all for today. Yeah, thank you. Bye.